reason for the statement?
Because fusion has more fuel
Okay.
than any other energy source that we know of.
Okay.
There is at least 30 million years worth. Okay, I'm sorry.
30 million.
There is at least 30 million years worth of fusion fuel
Okay.
in the oceans.
Okay. And in another 10 years, it is believed that the International Fusion Experiment, the ITR, will begin operating. Now, can you tell us a little bit about what this project is? It's promising large quantity of energy. So, if you could just explain us what this project is, what kind of reactions are going to take place, and how do you make some 500 million watts of energy?
So, what ITER is trying to do is it's trying to create the conditions where it is 10 times hotter than the middle of the sun
Okay.
in the middle of this device.
Okay.
So it's at about 200 million degrees.
Okay.
And at that speed, the particles that are in there, which are two kinds of hydrogen,
Okay.
deuterium and tritium.
Okay.
When deuterium and tritium crash into each other,
Right.
most of the time they just bounce off each other.
Okay.
But if they crash into each other hard enough, they get close enough
Right.
that something called the strong force, which holds the nuclei of atoms together,
Okay.
pulls them together, and they form helium,
Okay.
and they spit out a neutron.
Neutron.
And when they do that, they release lots and lots of energy.
Okay.
But you can't make it happen unless you can make them collide
Collide.
at great speed. And to
Okay.
make them collide at great speed, what you do is you heat it up to this temperature of 200 million degrees, and they're rushing around. Every now and again they bump into each other. Sometimes they fuse, and sometimes they just bounce off each other.
Okay.
And when that happens, they release all this energy. So the idea of ITER is to hold something at actually 230 million degrees will be the temperature right in the middle. And it holds it in a magnetic field, so it doesn't touch the walls anywhere.
Okay.
And then it heats it up from room temperature all the way up to 230 million degrees. And when it gets up there, it starts to fuse. This combining of two kinds of hydrogen to make helium, and releases lots and lots of energy. And ITER is designed to make at least 10 times more energy than it consumes. And it's designed to produce about half a gigawatt of power. That sounds like a lot of power. Half a gigawatt is about half a very large electrical power station.
Okay.
So it eats lots and lots of power, the kind of power that you would need to actually make electricity. But ITER is an experiment. So this will be the first time we've actually got to the point that it sustains itself and it can burn in this way that stars burn, because this is exactly what goes on in the middle of stars.
Okay. And is this like a continuous thing? Like, stars, the process goes on and on and on. So is this also a continuous process which will go on and on and on for years to come, or what is it?
So in our experiments, the idea is just to go and fuse the hydrogens, deuterium and tritium, together to make helium.
Okay.
In stars, it goes on further. It takes helium and it fuses it together to make carbon.
Okay.
And then when it's made carbon, it makes oxygen and nitrogen, and all the elements that are in our bodies came from this process in some star somewhere in the universe.
Okay.
We're made of elements that were made by fusion in the middle of stars.
Okay. So this experiment will go on for how many years?
We will start in 2019.
Okay.
And we'll probably start a little slowly because we'll have to get used to this very big machine. But by the mid-20s, we'll be doing full power shots this way. And hopefully when we've learned all we can learn from that machine in about 2030, we'll start building an actual power station from this. And so by 2040, we'll start that power station.
Okay.
And then by the turn of, about midway through this century, we will start building commercial power stations.
By 2050?
By 2050. It would be nice to go faster, but we only have a limited amount of money.
Right.
And we have to go at a scientific rate that we can actually prove what we can do and then move to the next stage. But one day, I believe the world will be powered by fusion power stations everywhere. You know, maybe there will be, I don't know, 50 fusion power stations in India.
Okay.
Maybe 100.
Okay. So we heard about this thing called tokamak nuclear fusion reactor. Can you just tell us what exactly this nuclear reactor is?
So,
and is this the one which you are building right now, which construction is going on?
ITER is being built,
Okay.
and that is a tokamak reactor.
Okay.
Tokamak just is a kind of way to hold it with a magnetic field.
Okay.
What you try and do is you try and push on this very hot gas of hydrogen, which is fusing, and you push on it with magnetic fields to keep it from touching the walls.
Walls, okay.
Because if it touched the walls, it would melt the walls.
Right.
And so you hold it in this cage of magnetic field. And that's that device, this particular kind of cage, is called a tokamak.
Okay.
And it was invented by the famous Russian dissident, Andrei Sakharov.
Okay, okay. And we've been reading that this, the ITER will generate some 500 million watts from 50 million watts. Is that a correct figure?
Yes, so we're going to put in as much as 50 million, but maybe less, depending on whether we need to put that much in. And we know we'll generate about 500 million, which is half a gigawatt, half a billion watts of energy. We have made 16 million watts in the device in my lab in the United Kingdom. That's called JET, which is a mini version of ITER. It's half the size of ITER. When I say it's mini, it's a very big device, but it's half the size of ITER. And it's not big enough to actually sustain itself. Whereas ITER will get to the point where the heat from the fusion will keep it hot. So it's like lighting a fire. When you first light a fire, you strike a match, and you put it to the fire. But when the fire catches, it keeps itself hot, and it keeps itself burning. And what you do with fusion is you have to heat it to start with, and then it starts heating itself. And once it starts heating itself, you can start to take away your heat. And maybe, if we're lucky in ITER, we can take all the heat away, and it'll make 500 million watts and consume no.
Okay. So you're saying we'll take the heat out, and that would be used to produce electricity.
Yes. In a way, it's a bit funny because fusion makes heat, and you use that heat to boil water and power a steam turbine. And so in a funny way, it's a very sophisticated steam engine.
Okay. Can you tell us why is fusion energy better than, say, the nuclear power plants or the coal or the thermal waste power plants?
Well, it's certainly better than coal because it produces no CO2. It's also better than coal in that maybe we have 200 more years of coal, but we have 30 million years of fusion. So it'll last much longer than coal. Compared to conventional nuclear power, fusion produces less waste. It's safer, and it doesn't involve the production of elements that are dangerous.
Now, what are the kind of waste material that comes out of a fusion reactor?
So the reaction creates helium, which is not a dangerous waste. And it produces very little of it, so it could just be released because there's plenty of helium in the atmosphere. It also makes a little bit of radioactivity in the steel around it. And we have designed a special steel in which the radioactivity doesn't last a long time. It lasts 1, 2, 3, up to about 10 years. And it decays very, very quickly. And therefore, you can leave it for 10 years and it will have decayed enough that it's low level. And if you leave it for 100 years, it becomes only as radioactive as coal. So not radioactive at all, really.
And the steel is the vessel that you're talking about?
Yes, you have to have a vessel to keep the air out. And you have the magnetic field to hold the hot plasma in the middle. And the magnetic field is created by coils, by big superconductor magnetic coils in which you pass electricity and it makes the magnets and it pushes the thing into the middle.
So scientifically we are trying to say that we've already proved that it is possible to generate more energy, it's possible to get more output of energy than the input.
Yes, I think the key thing about this next experiment is that we're going to make a great deal more energy than we consume. The current experiment jet that's at my lab makes about as much energy as it consumes, so it's about 1 to 1. Well, that's not good enough, right? And you have to go to bigger. I think this experiment in France is one of the great experiments of scientific history, right? Because there's going to be a moment in about 2024, 25, when we run that device and we take it up to temperature and it starts to cook itself. It starts to heat itself. The fusion fire, that's the first time we really have a fusion fire.
That is 24, 25 you're saying?
Actually, I think it's more like 25, 26.
25, 26. And 2019 you're saying
it will start.
It will start.
But when you start a device, you want to go slowly, so you learn and you bring it up to full power by the mid-20s. And we should learn most of what we need to know by 2030. Then after 2030, we need to build the first electricity producing station, a demonstration that we can make some electricity. But I think the first real commercial power, where you make a lot of money, really will take till almost the mid part of the century.
Is electricity also part of ITER, or is that a separate thing?
No, ITER's going to make no electricity because we'll be constantly turning it on and off and doing experiments and trying to make it better. At the moment, we think we can make 10 times more power than we put in. But there are some new experiments on some of the devices around the world, on JET, and on a device in America, and some of the experiments that the Indians have been involved in. There's a very, very active fusion program here in India.
Aditya, they have made some Aditya fusion reactors.
Yes. With some of the results that we've got, there are indications, in fact, that ITER will work better than we expected. And then we will be able to turn down the input energy and maybe make 100 times more energy than we put in. And that will be really important because that means eventually we can make electricity that's cheaper. The better performing it is, the cheaper the electricity we'll make in the future. I think there are also maybe some smart ideas still to be had. I think there's probably some young people, maybe here today, who will actually figure out some things that the older guys haven't yet figured out,